Andrew, hello.
Hi, Graham.
Hi. So our next speaker is Dr. Andrew Richards, and it's another data from experiments talk. So Andrew is head of scientific computing at the Diamond Light Source project. So Andrew, if you're able to connect.
Yeah, so can you see the slides?
Yeah, thank you.
Okay, just get the right one. Okay, so hi everyone. So I'm Andrew Richards. I'm head of scientific computing and data management at the Diamond Light Source. Going to change, which for those of you that aren't so familiar with Diamond, is based in the Oxfordshire countryside here in the UK. So about 40-minute drive from Oxford itself. And this is a view of the Diamond facility. It's a third generation synchrotron used to support primarily academic research across a whole spectrum from life sciences and physical sciences, and also some commercial usage as well. But we also sit within a campus. But we also sit within the sort of broader Harwell sort of campus, which contains a number of other facilities as well, such as the ISIS neutron facility, central lasers, so on and so forth. Which we all kind of collaborate with, and particularly we collaborate with the STFC, the Research Council in the UK, which funds the Scientific Computing Department here on site, tagged as the LHC Tier 1 Computing Centre, which we also have close links with for the sort of development of some of our sort of current and future computing needs, which I'll touch on in due course. More particularly, there's been some newer developments on the campus recently, over the last few years, which particularly link into Diamond. So under the banner of Diamond, we also operate a number of electron microscopes under the banner of EBIC and EPSIC, EBIC being the life sciences side of things, EPSIC being the physical sciences side of electron microscopy. And we also have a relationship with, we are a partner in the Developing Rosalind Franklin Institute, which will be sort of influential or key in the future sort of development of techniques and detectors and those kind of things for Diamond in the future. So Diamond itself, as I said, is a synchrotron. We currently have, this is just a sort of schematic which gives some impression as to how it's set up, very much like any other synchrotron. We currently have 33 operational beamlines, all of which can operate independently and at the same time. So that forms part of the sort of basis for the data challenge that we face. And as I've said, we support research across a whole spectrum of activities. To do that, we are grouped internally into a number of different science groups. So we have particular groupings of beamlines within these science groups that you can see here on this slide, which allow sort of different techniques and approaches to be applied as relevant. As I said, we also have electron microscopy. So we currently have these two national centres, EBIC being focused on the sort of life sciences side of things, who are running more of the microscopes at the moment. So they in particular have 5 Titan Cryoses, which are the large data volume generators within that. And on a smaller scale, especially in terms of sort of the computing needs and data volumes, we have EPSIC, which is more focused on the physical sciences, so the sort of side of operations. What does this mean in terms of sort of usage throughout the year? So in a typical year, and this has been impacted in the last year because of COVID, but in a typical year, Diamond has been seeing around 12,500 visits. And even before COVID kicked in, 40% of those visits were actually starting to take place as remote visits, where people didn't actually physically come to site. They only sent their samples to site for analysis, and then would actually conduct the experiment remotely. That has somewhat increased over the last year. COVID drove work across pretty much all the beamlines to make them remotely accessible, so that we are now in a situation where pretty much most of the beamlines can be operated remotely with help from on-site staff to allow people to conduct their sort of experiments once the samples have been sent in. In terms of looking at it in terms of sort of perhaps starting to look at data volumes then, and how this sort of comes together. In terms of those visits then, it very much varies across the beamlines and the experiment types as to how much data is being generated per experiment. overall, what we were beginning to see, or what we are seeing, is roughly somewhere around sort of 50 terabytes per day. Is not an uncommon overall production across all the electron microscopes and beamlines. And it had led to, just before COVID, it's hard to say what the number is now, but it had led just before COVID to as starting to trend towards almost a petabyte a month in data generation across the facility. A peak month just before we all went into this new way of working was just under 700 terabytes in a month. And to date, we now currently have just under 30 petabytes of data in our archive, which is kind of seen in this graph on the right-hand side of this picture here. And we've kept all the data back over the last 14 years of operations. But you know, most of that data is being generated in pretty much the last few years. That's kind of a snapshot of where we are now. I'll touch on some of the sort of future expectations in some of the later slides. But one of the key things that's coming up is that there is plans to upgrade Diamond, sort of Diamond 2 upgrade, as it's called, around about 2025, which will have a significant impact on the data flows and data rates that we already see across the facility. So I touched on diverse demands across the different beamlines. The numbers here just give some sort of indication as to what that actually might look like at the moment. So these are perhaps the sort of the four of the main areas that influence computing decisions within Diamonds, from the MX area, the macromolecular crystallography, through the imaging beamlines, doing tomography, tychography type stuff, through to the electron microscopes. And they just give some sort of feel, depending upon the type of experiment that they are supporting, and the type of sort of, you know, how many samples per day they're going through, gives some sort of feel for how much data, how much raw data is being generated on a sort of, you know, daily sort of basis, experiment by experiment basis. But that's kind of where we currently are. But as we look ahead, particularly with Diamond 2, it's interesting to reflect on not just the fact that detectors are continuing to improve at the moment and are planned to improve significantly beyond Diamond 2, but will also be sort of able to perform at a higher rate once Diamond has actually itself been upgraded and is in effect producing more light to drive the detectors. But if we look at one of the sort of planned flagship beamlines for Diamond 2, which is known as a sort of ultra high throughput MX beamline, has the tag of KO4, then the sort of bit circled in red here is a particular interest, because it's not just the developments in detector technology, it's the overall development in terms of robotics and everything else to drive the high throughput nature of how many samples per day that they can handle. And a single beamline is planning on the timescales of Diamond 2 to move from doing around 1,200 samples in a week to doing over 3,000 data sets in a day. And that's quite a significant uptick in sort of, you know, not just samples, but then how much data that generates that we then have to deal with at a sort of local level. In terms of data flows, then there are in essence two sort of directions of data that flow through Diamond. So on this diagram, there's effectively a left to right flow of information and a bottom to top flow of experimental data. So the red arrows and the boxes going in left to right really illustrate what a user sees when they interact with Diamond, from the first moment that they interact with the UAS, the user administration system, submit their application, their proposal, their award of beam time, which leads to the creation of visit directories and everything else needed to sort of make the experiment happen, through to that basic set of information, metadata, if you like, going through the system, being stored in iSpy-B and ultimately ending up alongside the experimental data in the archive, and allowing things like publications to take place. In conjunction with, once the experiment does take place, the bottom to top flow of information in this diagram, which is the data flow of how data is actually collected from the detector, and how that then, through the various software stacks that are used to collect the data from the detector, manage and visualize that data, and ultimately produce some kind of output which means something to the researcher, which, you know, results in, you know, some kind of output, some kind of meaning to the data, which ultimately then ends up in the archive for future sort of preservation and reuse at some point in the future. So from a user's point of view, they very much see this kind of flow of data when they come and interact with Diamond. In their mind is going from the proposal through to a publication with the steps supported in between. And Diamond's role is to support all of these steps and to make sure that they can get from proposal to publication as quickly as possible. That's the sort of competitive advantage, if you like, of coming to Diamond as opposed to other synchrotrons. That's the kind of driving desire to make things as easy as possible to do. From a data point of view, it can be in a sort of very simple way simplified as, so on the left of this diagram, we have 30 odd beamlines in operation. What exactly goes into that end station in terms of the sample can vary from viruses, as shown in this example here, a sort of virus of particular interest over the last years, I'm sure you'll all recognize, through to people putting batteries or ice cream or other items into other beamlines that are suited to undertake different types of experiments. But the basic data flow from a computational point of view is the same. We have some kind of sample that we want to understand. That is placed in front of a detector. That detector generates data, and that's where the computing infrastructure in Diamond then starts to take over. They take the flow of data, the raw data from the detector. We aim to get that data as quickly as possible and as straightforwardly as possible into the central compute resources, where from there then, what the user really wants to do is to be able to start to visualize that data as quickly as possible. So we're not just talking about getting the data to some kind of central resource and then processing it at some point in the future. Across most of the beamlines, there is a desire to start to get near real-time feedback on data as quickly as possible. Now, on some beamlines, that can mean that you're actually generating near real-time feedback, helping the user to make sure that the sample's worth continuing with, that the sample's actually in the beam, all that kind of stuff within, say, 20 seconds or less. Within other experiments, it may be of the order of minutes or hours before you're getting realistic data back that allows you to understand whether the sample is worth actually continuing with. But this is a different challenge then, if you like, across the different beamlines. What actually happens in this process, I'll come into it in a little bit more detail, but from an end user's point of view, most of what they will interact with is a sort of predefined set of software, at this stage a predefined set of workflows that they will interact with that is developed by Diamond and supported by Diamond. And in a lot of cases, with experiments taking place remotely now, people are using No Machine. We support the No Machine NX service to allow people to remotely access Diamond, interact directly with the beamlines in the experiment, and use that to sort of visualize and manipulate the data in as near as real time as possible. And then beyond that, once the data has been collected centrally, we then have a basic policy where beyond 30 days, the data is then archived and it goes to the archive, which is run by our neighbors, STFC, the Scientific Computing Department at STFC. We effectively piggyback on the work that they do for the LHC to help archive our data. But from a user's point of view, that data is still accessible. So if beyond that initial 30-day period, they still want to process the data, they can come to the archive, self-service, extract data and continue to process that data, either back on Diamond resources, or increasingly part of the challenge is where we can help people to put that data to allow them to do further post-processing that doesn't rely on the central resources at Diamond. So to go through that workflow in a little bit more detail to understand some of the challenges, the first step of getting the data from the detector is to simply get the sort of raw data from the back of the detector to the central sort of storage. Over the last few years, most of our beamlines are slowly upgrading from 10 gig links to 40 gig links to the core infrastructure. Some detectors could basically have a detector, if you like, a control box in between, which captures the raw data out of the detector and then write it straight to the central file systems to allow that ongoing data analysis to take place. Increasingly, though, there are detector developments. We have our own detector. I picked this one because it's also called ExCALIBUR, so very relevant for today. We have a detector in development called ExCALIBUR, which in itself is made up of a number of individual panels. At the moment, the individual panels have 40 gig links out to the back of them, and there are 8 panels that make up the detector. And so those 8 40 gig links then connect to 8 individual servers. It's not just a case of writing the raw data down to disk. A certain amount of processing of that data needs to take place as well before it's in a state that it can actually be written to disk. And so we then have this fan out, if you like, where the raw data goes to these intermediate servers, and then they in this sort of fanned out way, write the data down to the central storage platforms afterwards. This is all designed to be a sort of scalable infrastructure so that as detectors continue to develop, this flexible framework, which is called ODIN, can actually be scaled up to handle sort of different developments. And on the timeline and on the sort of future development plans of ExCALIBUR, those 40 gig links are due to be changed to 100 gig links. So there will effectively be, for one detector or one beamline, 8 100 gig links coming out of the detector to go to this ODIN server farm, if you like, before it then gets written to central storage for further analysis and post-processing. Part of the challenge there in the data flow is that writing data to disk is one of the challenges, but if you want to start to get near real-time feedback on that data as well, writing the data to disk doesn't work. And so there is also developments going on as to how in-flight processing of data can be improved. And I think these are the kind of areas where, you know, Diamond still has some work to do and can continue to sort of look at what else is happening in other domains to sort of help in, you know, looking at what the best techniques and software stacks are that can be used to help with some of the sort of in-flight processing of data. So once it's gone past, once the raw data is coming out of the detector, user's perspective will be very much the next step up in the software stack. We'll be using a piece of software called GDA, a sort of generic data acquisition software. This is really one of the sort of core pieces of software that users either on-site or remotely would be interacting with to drive the experiment, change parameters which control how robots might be moving or what actually might be happening with the sample, to actually allowing them through embedded components of visualization software to look at actually what their sample may actually look like. So this is the sort of first point in the chain where the user would actually, during the experiment, be starting to interact with the experiment and being able to see what their sample actually looks like. After that, or as part of that, as I said before, it's all about helping people through this whole life cycle. And so beyond capturing the data, there is then a whole suite of sort of data analysis software, which may not then necessarily be part of an automated workflow. It may be more driven by individual users selecting which software they want to use to then further analyze data, which will then allow people on the systems that we currently provide to start to interact with the data, make use of it, make sense of the data, and ultimately come up with, you know, some kind of final result which they can use later in time. Why is this important in helping sort of things to get through? I mean, just to give some sort of feel, you know, in one particular area of Diamond, particularly in the MX beamlines, the life sciences area, you know, data that's generated here goes off to be deposited in other external resources, such as the PDB, the Protein Data Bank. And out of a number of synchrotrons around the world and Europe, Diamond is one of the largest depositors of resolved samples into the PDB database. Resolved proteins into the PDB database. And so making this pipeline as simple and as fast as possible is key in being able to do this and to be able to resolve and then deposit those results into these sort of national, sort of international sort of repositories for such data sets. In terms of the sort of data challenge though, it's, you know, as I said, the archive has grown to just under 30 petabytes at the moment. It's not just the volume of data as well. That 30 petabytes of data is currently made up of something of the order of 3 billion individual files. Compared to some similar archives of size, such as the Cedar archive, which is about, the last time I looked, something like about 25 petabytes. The last numbers I looked at, you know, the number of files they had was more of the order of 300, 400 million files. So part of the challenge we have, as well as not just the volume of data, but the number of files that make up this data sets within the archive. We currently support this through infrastructure, predominantly support this through infrastructure which is on site. So we operate 2 data centers. They have effectively HPC platforms in each of those 2 data centers. There's nothing particularly special about them in some sense. They're made up of traditional x86 cores, GPUs, increasingly, particularly in imaging and typography, GPUs are heavily used to help with the processing of data. And they're underpinned by approximately about 16 petabytes of data across the storage across the 2 data centers, which acts, if you like, as this sort of initial buffer upon which the data sits. The experimental data policy is for 30 days, but often data sits on disk for a lot longer than 30 days to allow people to continue to process their data sets. But the increasing challenge is that, you know, these systems to date that have been built on site are predominantly built for the data acquisition. If you cannot take the data from the detector and do something sensible with it or store it as quickly as possible, then you effectively stall the entire operation of Diamond. So when people want to subsequently start to post-process their data, and at the moment they've been doing that post-processing of data on the same platforms, then the two worlds compete with each other, and the post-processing requirements are the ones that suffer, because primarily these systems are here to support the data acquisition. So what we've been working on over the last sort of few years, we're starting to look at sort of how external resources, how the cloud might help us. We started off a few years ago with some of the very sort of basic aspects of, what does it mean to do burst computing? How can we make use of resources elsewhere? We're, collaborating as part of the IRIS infrastructure to sort of, see how we could make use of their OpenStack deployments, etc. We'd had discussions with commercial providers, Amazon, Google, etc., to look what we could do there. And this led within the sort of last year or so to starting to make sort of more progress in-house with an on-site, sort of an on-premise Kubernetes-based cluster to allow people to become much more familiar with cloud technology and to look at what it means to move workloads around between on-premise and off-premise infrastructure. But also, one of the things that I've done recently is that within the last year, I've defined a sort of technical roadmap, which is starting to, and it might look very sensible and obvious at one level, but starting to drive the sort of need that things have to be better separated out within Diamond. So starting to define an operating model where, you have defined platforms which have specific roles to do, and then looking at where those platforms are best located. So things like the data acquisition platform will always have to be closely coupled to Diamond itself and to the operation of Diamond. It's there to support that immediate capture of data and immediate analysis of data. But once you go beyond the experiment visit and people want to continue to sort of do post-processing, then how do we move data to other locations? And it's not just putting hardware elsewhere, it's getting the software and the software developers and the workflow developers to actually appreciate the fact that not everything continues to live in one or two data centers, and how you make use then, or how you enable things to move through use of things like containerization and other approaches. How do you sort of enable workflows to go elsewhere, into the IRIS platform, into commercial cloud providers, or to allow people to take things away more to their own institutes and use their own platforms at their own institutes to allow them to do the sort of further work that they want to do. And then finally, just to sort of finish off in sort of the overall challenges, one of the things that has changed in the last couple of years, and we have 12 months to go to figure out some of the final needs for this, is that Diamond changed its data policy, its experimental data policy a couple of years ago, so that all data captured in the last 2 years is now currently under an open data policy. It's a 3-year embargo period, but on the 1st of April next year, 2022, Diamond will start to have the right to make data sets openly available. And what it means to make data openly available, not just accessible from the archive to people who originally created the data, is something that we're currently grappling with. What it actually means to have an open data repository, what the most appropriate platform to sit it on, what the most appropriate interfaces to provide to users are, and also what demand there might actually be for accessing data, is something that we need to sort of understand and sort of look at how best it's addressed. But this is something that will, continue as the data volumes continue to increase, be something that, we sort of have to work on in terms of that end-to-end data flow and what it means to then make the data available, and whether we support external users who may not have originally been Diamond users to process data, or whether we just make it easy for them to take the data away to somewhere where they can process it or pay to process it themselves in some way, shape or form. So, I think that's sort of, basically what I wanted to cover today. We're nowhere near the scale of the SKA in terms of data volume, but doing some forward prediction of where we might be by 2030 with the Diamond, Diamond 2 upgrade. We currently have 30 petabytes of data in the archive today. By 2030, the estimate is somewhere between half an exabyte and an exabyte of data in the archive if things continue to go in the direction that we see them go. And so, these are some of the things that, we sort of want to consider and work with the community to better understand. So I'll finish there. It's a bit of a quick run through of what we do and how we operate, and hope that was useful.
Thanks very much, Andrew. Yeah, it's just some questions in. So one from Sean. You mentioned how many files you have in your archive, and the question is, does that impact on the ability to search and retrieve what you need?
It's a good question. So we've been doing a lot of work with STFC over the last few years through a project called the Diamond Data Store project, to understand what the future archive needs to be and how it scales. And at one level, a lot of the testing work there has been to sort of prove that it can scale an archive with the volumes of data that we need to do into the future, and how the interface to it actually needs to be improved to be able to search and find data. It is a good question. I mean, at the moment, people who come to the archive tend to know what they're looking for, because they're the users, they're the people who are associated with the original visit. Once this becomes a more open repository and people want to come and perhaps find stuff that they don't know what they're looking for, then that is an interesting question. I'm not sure we have the answer yet. There's people like Alejandra Gonzalez Beltran in STFC who are strongly leading on this for Diamond as well. I can see they're in the guest list, and would be very useful to answer some of these questions if people have them in the future, but we could happily have some discussion around that.
Yeah, I had a question around the challenges you were talking about, openly available data, and you also, maybe this is not connected, but I just connected it. You mentioned Jupyter notebooks as well, and on another slide. Is that something there are just so many different interfaces you could have onto this data, and as you say, different levels of expertise of the user.
Yeah.
If you could sort of comment on any of that, Andy.
So we haven't done work to connect those two ideas yet in terms of using the Jupyter Hub work for actually accessing the open data. I think the open data discussions are far more immature compared to that. The Jupyter Hub work has been very much focused internally at the moment on existing Diamond users and Diamond staff, to allow them to access that as a platform, to allow them to sort of do the sort of experiments and to sort of play with things in the way they want. It was one of the kind of early adopters of the on-premise Kubernetes cluster to be able to run Jupyter notebooks to allow people to just kind of play around with things and do what they want. But it's been very much internally focused first, rather than as part of any opening up of data externally.
Okay, thanks, Andy. Question here from Norbert Podolsky. He's wondering, have you looked at Adios, which is something out of Oak Ridge?
No, we haven't. No.
I think there'll be an opportunity to learn more about that in Scott's talk at 2:40. So any other questions from the group? Otherwise, thanks very much, Andrew. Very nice summary and introduction to Diamond and challenges there.